Welcome to this lecture series entitled The Fundamentals of Ultrasound Physics, put together by the Honors Ultrasound Group of The Ohio State University College of Medicine. The title of this lecture is The Physics of Diagnostic Ultrasound. Many of the topics covered in this particular lecture form the fundamental basis for future lectures to come, including topics such as transducers physics, pulse echo ultrasound, Doppler ultrasound, including color flow imaging, as well as image artifacts. We'll start off by discussing the phenomena of sound as a wave, as opposed to sound being a particle. Many of the properties of sound, such as amplitude, frequency, etc., are determined primarily by the properties of the medium it traverses, such as material properties in the form of density and acoustic impedance. Acoustic impedance, in turn, has significance in determining the reflection and the transmission of the initial ultrasound wave. Refraction of ultrasound against a interface is also very important and will be discussed. Acoustic scattering, on the other hand, is present in many soft tissues of the human body. We'll discuss the physics behind it as well as the advantages it presents. Finally, attenuation will be discussed in detail as it relates to the dying down of the initial ultrasound signal as it traverses deeper and deeper into the tissues. We'll discuss what can be done to compensate for this phenomenon. The entire sound spectrum consists of infrasound, audible sound, and ultrasound. Audible sound ranges in the frequency between 20 Hz to 20 kHz, which is what we experience during normal living. On the other hand, ultrasound is defined by any sound wave with a frequency over 20 kHz regardless of orientation. Therefore, unless we have characteristics of a bat, we typically do not detect ultrasound. However, during the Doppler measurement employed during a vascular study, for example, oftentimes we can hear audible sounds because the Doppler frequency falls within the audible range. Diagnostic ultrasound consists of probes that have frequency ranging from 1 MHz all the way up to 20 MHz. Abdominal probes typically have lower frequency range, whereas vascular probes can be upwards of over 10 MHz or more. Unlike electromagnetic waves, sound depends on a physical medium for propagation. Therefore, sound cannot travel through a vacuum. From here on out, it is instructive to think of sound waves as energy. As an ultrasound beam traverses the body tissue, think of the sound wave energy being dispersed, refracted, reflected, transmitted, and absorbed. Having this understanding will serve you well for future lectures to come. How is ultrasound generated, one might ask? In modern medical ultrasound machines, a piezoelectric transducer is responsible for the generation of the ultrasound beam. In a future lecture entitled Transducers Physics, we'll go behind the phenomenon and explain in detail the piezoelectric effect. Sound is a wave with a defined speed, periodicity, frequency, amplitude, intensity, and direction. As we mentioned previously, it requires a medium for this mechanical wave called sound to travel in. The compression or pushing together of the molecules within the medium causes the kinetic energy to be given off by the molecules as they press against each other. Thus, the sound energy travels outward from the source of the original ultrasound beam. Sound travels through air, water, and even a block of steel. In air, the speed of sound is 330 meters per second. In the next picture, you see a picture of a fighter jet breaking the sound barrier. However, it's interesting to note that in soft tissues, ultrasound actually travels at a much higher speed of 1,540 meters per second. This makes it traveling close to Mach 5. On the other hand, sound wave velocities are almost 5 decades slower than electromagnetic waves. So therefore, this needs to be taken into consideration. An example of mechanical waves, besides some sound waves, include ocean waves and seismic waves. On the other hand, electromagnetic waves include participants such as radio waves, RF waves seen in cell phones, X-rays, and light. Sound waves can be longitudinal or they could be transverse. In longitudinal waves, the wave action is parallel to the direction of the structural vibration. In medical ultrasound, only longitudinal waves are important. As is seen in the next figure, the blue molecules representing the medium, as they are influenced by the incoming sound waves, do not actually move. However, they do oscillate about their equilibrium positions. In the picture, they're depicted as moving left and right of their equilibrium position. On the other hand, the sound waves propagate going from left to right, and therefore they are termed longitudinal waves because of the same direction. On the other hand, for transverse or shear waves, while they're in theory possible, they're certainly not useful in the transmission of ultrasound in the body tissue. They can be understood as having the medium, the molecules going vibrating inside and outside into the paper, with the sound waves going left to right. Lambda and P pressure amplitude are the key variables characterizing the sound waves. Compression and rarefaction describe the pushing together of the molecules or the spreading apart of the molecules inside the medium as they're influenced by the sound waves. Compression is a snapshot in space where density and pressure are elevated. On the other hand, rarefaction is the exact opposite, where the density and pressure, due to the sound wave exertion on the material medium, are depressed. This diagram depicts the density of the molecules of the medium corresponding to the sound wave amplitude. Where there's compression, the amplitude is increased, whereas there's rarefaction, the amplitude is minimum. The direction of the sound wave propagation as it traverses through the medium is depicted by the following diagram. As it moves from left to right, you can see that the density of the molecules within the medium correspond to the sound wave's amplitude. Several more definitions are in order, namely period and frequency. The period T is the time it takes for the disturbance to repeat itself within one cycle. On the other hand, frequency F is the number of times per second that a vibrating particle goes through the original position. T is inversely proportional to frequency, as is depicted by this equation and the diagram showing the sound wave as a function of time with T as the definition of the period between peak to peak. Let's do a question. Suppose the ultrasound wave has a frequency of 5 megahertz. What is the period? Is the answer A, 1 second, B, 0.5 microseconds, C, 0.2 microseconds, or D, 0.5 milliseconds? You may pause the tape. The correct answer is C, 0.2 microseconds. Bear in mind that the period is equal to 1 over the frequency, which is 1 over 5 times 10 to the 6 hertz, which gives you 0.2 times 10 to the minus 6 seconds, or 0.2 microseconds. The speed of sound is a very important component for the understanding of ultrasound in terms of the pulse-echo reflection and propagation. It is determined, as we mentioned previously, by the properties of the medium. The equation C, standing for speed of sound, is square root of B, which is the bulk modulus, over rho, the density of the medium. The bulk modulus denotes the stiffness of the material, which oftentimes is the determining factor for the speed of sound. On the other hand, rho, the density, is typically close to 1 kilogram per cubic meter for most substances. The materials of interest, denoting the bookends of the speed of sound, range from air at 330 meters per second to 600 meters per second for lungs, which is the lowest speed of sound for a biological tissue due to the presence of air-filled alveoli, and bone of 4,000 meters per second. On the other hand, fat, water, liver, and muscle, they all fall within a very narrow range for the soft tissue speed of sound, and are therefore a relatively good sign in terms of ultrasound applicability. Note that if there's an excessive speed differences between interfaces, that will lead to poor ultrasound resolution. Let's discuss wavelength. Wavelength is defined as the distance between 2 points in a wave. For example, the distance between two peaks or two valleys of a sound wave, is defined as wavelength. The equation lambda equals c divided by f. C is the speed of sound in the medium, and f is the frequency. There is an inverse relationship between lambda and f. Let's do an example. If c is 1540 meters per second, and the frequency f is 3 megahertz, what is the wavelength lambda? Lambda equals 1540 divided by 3 times 10 to the 6 hertz, equals 5.1 times 10 to the minus 4 meters, or 0.51 millimeters. A better equation to remember for this kind of calculation in the future is this. Lambda is 1.54 millimeters divided by f expressed in megahertz. This will give you a quick understanding of the magnitude of lambda that you're dealing with.